Lecture. And today's lecture is, as it says here, process scheduling. We're actually now going to start talking a little bit about some basic algorithms for choosing which process will get the CPU. That's one of the things that the operating system has to do. It is to allocate resources in a fair and equitable way. Now, fair and equitable can be defined in different ways.
The DEI computers.
Kind of. We have to, yes, the DEI computers. So let's get started. Objectives, you can read on your own here. So basically, the basic concept that you have to know here is that there's such a thing as a CPU burst and then an IO burst, which means that the computer, if you think about what a computer does, running, doing calculations, then it says cin, or it says please, it says get string, it's asked for some input from the user, or it asks to read from a disk, and then it waits for the user to type something. And of course, the time it takes for the user to type something from the perspective of the CPU is astronomically large amount of time until the person finally types whatever he types and hits enter. And then the computer can again go running until it again wants some input or output, either from the disk or from the keyboard, something like that, or to print out something. So the computer essentially alternates between using the CPU and waiting for an IO device to give it some information. So maximum CPU utilization is obtained with multiprogramming. What does multiprogramming mean? It means wouldn't it be nice if when one program is doing a IO burst, another program can come and use the CPU at that time. And then when he wants the CPU again, the other one will be an IO. And we can sort of interleave these two programs to have them run at the same time. Okay, so process execution consists of a cycle of CPU execution, IO wait, CPU burst. So we explained all that. Fine. So that's what we see in this picture, waiting for IO, store and increment, whatever action it's doing, and then all of a sudden write to file, IO again. Load, store, add, store, read from file, another IO. Okay, so now we can look at, this is a kind of interesting diagram. It's showing you burst durations, and it's showing you that most burst durations are relatively short, whatever, this is in milliseconds. So most of them are much less than 8 milliseconds. Some of them can be longer, but there are a few of those. Okay. And this is our familiar diagram we've seen before of the states that a process can be in. And we'll see why we need this, but essentially the ready queue is where the process is waiting. The scheduler is the one who's in charge of saying, okay, now it's your turn to get the CPU and go to running. When an IO event happens, then he goes to waiting for the IO. When he comes back from the waiting, he doesn't go back to running immediately. He goes back to ready, and the scheduler will choose to schedule him or schedule somebody else according to whatever diversity, equity, and what is it called? Inclusion rules should dictate for him. So the CPU scheduler. The CPU scheduler selects from among the processes in the ready queue, like we just said, and allocates the CPU core to one of them. The queue can be ordered in various ways, and we're going to discuss in today's class those various ways. So here's an interesting thing. CPU scheduling may take place when a process switches from running state to waiting state. That's why I have a picture here. When it goes from running to waiting, so why is there CPU scheduling now? When it goes from running to waiting, it's in waiting. Why is that? It says in the previous, right? There's 4 conditions where you may have scheduling. So first it's switching from running to waiting. So why is that? Running to waiting. Now, why do I do CPU scheduling here?
You can take it out of the CPU, put it in the waiting. You can put something else in.
Because something else can go in. Because if he's gone out of the CPU, then now I need to schedule. I got a whole list of people over here. The schedule needs to take action. What's the second case? Switching from running to ready state. So if it goes from running directly to ready, which is not waiting for an IO, this is possible. That's what this diagram means. An interrupt happened. Something told him stop running. One reason to stop, well, there are different reasons to stop. Some interrupt came and said stop running. He'd like to keep running. He's not doing IO. He'd like to keep running, so he goes to ready. So now again we need to do we have to do some kind of scheduling. What about if it switches from waiting to ready? What about if it switches from waiting to ready? Do I have to do scheduling now? Well, it depends. No, not necessarily. Because remember, he was not using the CPU. It could be that process number 3 is using the CPU. Process number 2 has gone from waiting to ready. He's now ready, but 3 is still happily using the CPU. We're not going to do any scheduling activity now. But it could require scheduling. Why would it require scheduling? Because it could be we have some kind of priority. Maybe 2 came in here. Oh, he's high priority. We're going to kick out 3. So when we go from waiting to ready, we don't necessarily have to do scheduling, but we could. If we would do scheduling at that point, it would be called preemption. Because we'd be preempting this person. With this process here, sometimes I call the process people because I think of them as my children. So this process, in my yeah, I hope hopefully none of my processes will be orphans. This goes from running to waiting. When it goes from waiting to ready, if I preempt this guy, he was happily running. If I preempt him, that's why, and then I do scheduling. So if you schedule when you go from waiting to ready, that's called preemption. Well, 4th case is terminates. Why would I do scheduling if a process goes from terminating? Well, that's kind of obvious, right? Why process goes from running to terminated? Why do I do scheduling? Because the CPU is now available. CPU is available. He's no longer running. So somebody should go in. Yeah, okay. So it says like this, for situations 1 and 4, there is no choice to schedule. So in terminate, I got to choose somebody. And in 1, if the process goes from running to waiting, then I got to schedule somebody, otherwise CPU is just sitting around doing nothing. But why, what about 2? So I just switch from running to ready. Why do I not necessarily have to do this? There's no choice to schedule. A new process when exists in the queue must be selected. Well, I guess technically, in case 2, a new process doesn't have to be scheduled. I can reschedule the same old one. You can go from running to ready and then go back to running again. So I guess technically that's what they mean. There is a choice. I'm not sure exactly why not do. For situation 2, however, there is a choice. Because I guess what they're saying like this, when for 2 and 3, why is there a choice? Because I went from running to ready, yeah? So now I've got people in ready, I gotta choose who of the ready ones to do. And also from waiting to ready, I could choose not to schedule anybody.
I didn't understand why is 3 scheduling? So it's switching from waiting to ready.
From waiting to ready. Yeah, right, it should be really, it makes more sense that it should be 1 and 2, really, not 1, it should be, sorry, it should be, what are you saying? Why is from waiting to ready scheduling? Because when a new person comes into scheduling, it's true that nobody left here, I could leave him there. I have a choice, but I could do scheduling because, for example, this process that came from waiting could have a high priority. In which case I want to kick out the guy who's got the CPU. The guy who's got the CPU, all of a sudden I'm finding out that this process isn't ready. He's super high priority, kick out everybody from the CPU, let him go. So I could do scheduling in that case. So it's true, but I don't have to. I mean, because depends on my schedule. And 2 also. Why in 1 from running to, I guess I mean, I have a choice of who to schedule. I don't know what they mean by choice. It's a little bit strange term. Actually, I just checked in a different version of the book, it doesn't do a choice here. Well, let's go on. But when scheduling takes place only under circumstances 1 and 4, scheduling scheme is called non-preemptive. Otherwise preemptive. So 1 and 4 are called non-preemptive. Why? Because in terminate, so I didn't have to preempt anybody to start scheduling. And in case 1, if a process went from running to waiting, he went to waiting anyway. He's not interested. So I'm not preempting anybody. Right? That's non-preemptive. So I have, in other words, I have to schedule somebody because the CPU is now available. But if a process goes from. But here, what does it say? Otherwise, it is preemptive. If in 2 and 3. If it's going from running to ready.
But then, that doesn't make sense to me,
Because how did I get there? If I went from running to ready, you see, this is the point. If I managed to have a circumstance when I went from running to ready, that meant I did some kind of preemption, was why he was happy. He doesn't want to go to waiting. He doesn't want to go to terminate. He wants to keep running. And I put him in ready. So I preempted him. So that's called preemptive.
But wouldn't you go from one running to ready like when you're done with your CPU time?
Yeah, but that's called preemption. If my CPU time, if we're using a time slice.
Yeah.
We'll see that's called round robin. If we use a time slice, then that's called preemption, because that means 200 milliseconds have gone by, preempt you, stop you, and let somebody else go. So if we went from running to ready, how did we get there? It must be that there was some kind of preemption that got us there. So that's preemption. And also in 3, switching from waiting to ready, if from waiting to ready, it's true that wasn't a preemption to get there. But if I would now schedule at this point, that would mean I'm doing some kind of preemption. That would, the only reason I would schedule it because of this event would be because of priorities. And therefore I'd be preempting this guy who wants to keep running. So that's what they really mean. I'm not sure if I like the word choice there, but the point is, one is called preemptive and one is not. Under non-preemptive scheduling, once the CPU has been allocated to a process, the process keeps the CPU until the process itself, releases it by either terminating or going to waiting. That is, I get the CPU for as long as I want. That's called non-preemption. Because I get to keep it as long as I want, unless I don't want it anymore. I died or I went to waiting. Virtually all modern operating systems use preemptive scheduling. And the main one that we talked about before is time slots, which is called round robin. Preemptive scheduling can result in race conditions when data are shared among several processes. Because the question is, when do I preempt him? What if he was in the middle of doing something very critical? Let's say 2 processes are using the same bit of data. And he was just about to write something to it. And then the other process grabbed the data and changed it. Now, if he had known about that change, the first process maybe would have changed it in a different way. But he didn't. And so now when it comes back to the first process, he'll put it to what he wanted to. But like, for example, well, we'll see an example. Consider the case of 2 processes that share data. While one process is updating the data, it is preempted so that the second process can run. The second process then tries to read the data, which are in an inconsistent state. In other words, he was in the middle of updating something. Maybe he changed the first name, he didn't yet change the last name. And now somebody reads it and he gets a mixed up name. There is no such person with that name. This issue will be explored further. Okay, so that's a sort of a tantalizing little mention of a problem of race condition, but we didn't really get into it. We'll get into it. Dispatcher module gives control of the CPU to the process. Right. So notice here, executing P0, that's process 0. And here executing P1. Why don't we go straight from P0 to P1? Well, there's some things we have to do in the middle, and that's called dispatch latency, which is the time it takes to stop one process essentially and start the other. The main thing we have to do is save the state of the process into the PCB. Remember in the lab, actually, we saw twice how in the RAM, there's data for each process. And if the registers have changed as the process was running, so then the values in the PCB have to change. But we don't do that every time the register changes. We do that at the time of the switch. When we switch, we call it a context switch. When we switch from one process to the other. So that's these 2 white boxes here, where we save the state into the PCB, and then we restore the state that had previously been stored. We restore PCB 1.
Didn't we have some other functionality that did that, not called the dispatcher? That saved the state of the previous register and then
No, that's called dispatcher.
it's just
It's called switching context or context switch. Switching to user mode. right? We have to jump to the proper place in the, these actions are done in super user mode. But then when I finally want this program to start running, I gotta go back to user mode, because he's a regular program, not the operating system. And I've got to change the program counter to start this program at the right point. So dispatch latency is this time. It's also called context switch overhead. It's the overhead for our context switch. So, and before we discuss the algorithms, so wait a second. So what have we said so far? We said so far that there's preemption is non-preemption. We said that there's such a thing as dispatch latency, because it's a certain time. Obviously, we don't want, here's an interesting point. We want this, what should the relative size of the dispatch latency be to, let's say, the time slice? If we chop processes every set amount of time and make another process go, what should the relationship between this time and the time we give to the process to actually run? Once he actually gets to start running, how much time should he get in relation to this time? Significantly more. In other words, we don't want it to be that this is 50% of the time of the, right? We don't want that this takes 10 minutes, this takes 10, microseconds, and this takes 10 microseconds. And the running is 10 microseconds. It would be half the time we'd be doing nothing but switching processes. We want it to be that if this takes 1 microsecond, this maybe takes 200 microseconds. So that we don't spend all our time doing this overhead. So when we're talking about criteria for evaluating algorithms for scheduling processes. We have different algorithms and we want to be able to compare them. So these are 5 criteria for evaluating them. One is called CPU utilization. Well, that's not really a criteria, but in general, yeah, we don't want CPU. I mean, it is a criteria, but we will talk about it less. We want the CPU to be busy all the time. We don't want it to be, let's say, for example, somebody went to I/O and then we just waited around anyway. And the CPU did nothing and didn't schedule another process. We want the scheduler to be active. We don't want him to just like ignore a situation when the CPU is idle. Throughput. Throughput is a measure where the number of processes that complete their execution per time unit. In other words, how many processes can I complete their entire execution? Which means they may have many CPU bursts, I/O bursts, CPU bursts, I/O bursts, but over the course of a day, how many, or over the course of an hour, how many processes can go start to finish? If one algorithm gets more processes through start to finish than another, then that algorithm is better. Another measure is turnaround time, which is the time to execute one process. How much time a particular process takes to run. We could also talk about the average. How long is the average process taking to run? That's a different thing. This is how many, the first one is how many processes I can get done in X time, in a day, in an hour, in a minute. This is how long does the average process, or how long does a particular process take to get finished. The third criteria, which is in some ways the most easy to calculate and easy to think about, is called the waiting time or wait time. Amount of time a process has been waiting in the ready queue. We want to see here, we want to maximize throughput. We want to maximize, well, turnaround time, no, throughput we want to maximize. Turnaround time, we want to minimize. Wait time, we also want to minimize, because that's the time that the process is doing nothing. The process would like to get the CPU, but he can't. Now, we're not going to count the time that he is waiting for I/O. That's not the wait time. The wait time is the amount of time he's waiting in which queue? In the ready queue. He'd like to get the processor, but he can't. We want to minimize the wait time. Response time is another measure, which is the amount of time it takes from when a request was submitted until the first response is produced. Not output, for time. It's only for time sharing records. Response time we're not going to talk about so much, but it basically means, will I get a response? I started running the program. Will I see that it started running? Let's say I throw it into the system and it doesn't get, it gets no attention. It's kind of like when you go to the emergency room, there's somebody who comes and says, "Oh, what's your name?" He takes your phone number and your blood and your pulse and then you feel like, oh, I'm in the system. They know who I am, and then I have to wait 6 hours before I see anybody. But at least I got some response from the system. That would be response time. When do I get my first response?
There's not an amount, it's yes or no.
No, the amount of time it takes before that nurse comes and measures my blood
Not
pressure.
if they come, not.
Not if they come, no. Time. Okay. So here's what I just said before. We want to maximize CPU utilization, maximize throughput, minimize turnaround time, minimize wait time, and minimize response time. Fine. So here is our first algorithm, which is the simplest and easiest to think about. First come, first serve. You've seen this algorithm maybe in other places. Like it's basically a queue, which is the opposite of a FIFO, right? First in, first out. First come, first serve, first in, first out, same kind of thing. It's a FIFO. So this is a Gantt chart, and we'll be looking at Gantt charts. And the idea is like this: we have three processes, P1, P2, and P3, and their burst times are known somehow. Somehow they're known, or somehow they're known, or let's say they turn out to be these things. And the first one to come was P1. So he goes in, they all came, let's say they all came. This is a kind of a weird circumstance, but we're saying like this: they all came at the same time, but P1 came first. Because nothing can actually be at the same time. So they all came at time 0, but there's a certain order. In fact, sometimes we'll say they all came at time 0, and they say, well, how should I know which one came first? So the rule is, in all your exercises that you'll do, the rule is that the P with the lowest number, the ID number that's the lowest, is considered to be the first. So in this case, if they all came at the same time, P1 came first. He'll be serviced first. And then P2, and then P3. So now let's calculate the average wait time. Well, the wait time for P1 was 0. The wait time for P2 was 24, and the wait time for P3 was 27, whatever units this is. So we add up 0, 24, and 27, divided by 3, and we get 17.
What does 17 represent?
17 represents the average wait time. Some of them wait nothing, some of them wait 0.
Aren't these the P1 equals 0, 24, and 27, aren't those the times that they start waiting? Or is it?
No. They all started waiting at time 0. They all start waiting at time 0, they come at time 0. So they're all waiting at time 0, except one guy, P1 doesn't wait at all. So his total wait time is 0. P2's wait time, he goes immediately after P1, so he had to wait for P1 to finish, so his wait time is 24. And poor P3, he had to wait for both P1 and P2 to finish, so his wait time is 27 before he finally got to run.
Thank you.
Now we see that the average wait time will be the sum divided by 3, which is how many processes there were, and we get 17.
Thank you.
Now, what's interesting about this is that if they had come in a slightly different order, for example, suppose that even though they all came at time 0, P2 came first somehow. P2 was the first one at time 0. So then P2 would go first, and then P3 came, and P1 was the third one to come. So then we'd recalculate it, and we say P1 had a wait time of 6 because he didn't start till 6. He didn't start till time 6. He had to wait for P2 and P3. P2 had a wait time of 0 because he was the first one to be serviced, and P3 had a wait time of only 3. So now if we add the wait times, we get 6 and 0 and 3 is 9, divided by 3 is 3. Much better than the previous case. Yet we're using the same algorithm. So this algorithm is like sort of inconsistent. It depends very much on whether we let the big guy go first or last. If the big one goes first, then everybody has to wait for him. If the big guy goes last, then we got some people not to have to wait. In other words, right? It's kind of like if you come to the doctor and there's 3 people waiting maybe, and he'll say, well, you I can take care of in a second, you I can take care of in a second, and you will be an hour, so I'll take the 2 for a second, and I'll get you guys into home. At least you guys don't have to wait. And the other guy will wait a little bit, but he's not waiting so much. That would be a good doctor. Most doctors don't do that. They just take you as you come, and I'm waiting for 3 hours for this one guy to finish, and I just need him to write a prescription for me. It takes a second. And there's no way of him knowing, of him scheduling me ahead because I'm shorter. So first come, first serve doesn't claim to look at these numbers, at the size of the, it just says first come, first serve. I am not going to look at how much time you need. In fact, I don't really know. A process comes, I have no way of knowing ahead of time how much CPU time he's gonna need. Remember, it's how much CPU time he's gonna need before his first IO. He'll need many times, but this is just in one instance. So this algorithm has this problem of like, let's say, inconsistent results, depending on the exact order that they come. Now, there's a concept here which is called the convoy effect, which is essentially in the previous case, the ones behind had to wait for the first one. So it's like when you have a convoy, let's say, of trucks going up from Tel Aviv to Jerusalem, and the slowest truck goes at 10 miles an hour. How fast do all the trucks go? 10 miles an hour, because otherwise what happens? You don't have a convoy. If you let the faster ones go ahead, then you're just on a convoy. And you can say, well, only if the first one is the slow one, like in our first case, like in the other case. When the first one is the slow one, then they all have to wait. But here they didn't have to wait. But there is a kind of convoy. First of all, we don't know, we can't know the future. We don't know what these, we don't necessarily know ahead of time what these numbers are, and that's not our algorithm. Our algorithm is first come, first serve, so we don't care what their uses are. We're going to do first come, first serve. So we're going to suffer from this convoy effect. The interesting thing about the convoy effect also is that what if you say, well, we'll do it this, what had happened to me this way? Is there a convoy effect here? No, you say. Yes, but let's say P1 is a consistently heavy CPU user. He's calculating all kinds of heavy things. And P2 and 3 are not. So even if you got lucky the first time, then let's say that during this 24 microseconds, P2 and P3, and it's true that they went to IO, but they finished their IO very quickly. And they got right back online. Who are they gonna have to wait for? P1 again. So even if you had this ideal circumstance that the first two were short, but they're gonna quickly go, they're gonna go to IO, and then they come right back to the queue, and now they're still waiting for this long process. So even if you get lucky the first time, the second time you're gonna be waiting, you might be waiting for him again. So that's called the convoy effect, that if there's one guy who's slow, it'll slow down everybody, even if you got lucky the first time.
Do we have a method of like?
Dealing with that?
Yeah,
we have other algorithms. We have other.
Like stopping process one, so that's priority. Process
Exactly.
two.
So, well, if we would have a time slice, which we'll get to, that's called the round robin algorithm, a different algorithm, then we could chop it after 10 seconds, then nobody would ever get more than 10 seconds, and then it would be fine.
Thank you.
That would be another method. Sure. So here's the first idea. This would be great. Shortest job first. Let's just have an algorithm that no matter what happens, we put 2 and 3 first, even if they come after. Well, that'll be a little bit of a problem, because
Still have the convoy.
We have to get to people.
There we go.
if P1 already got, well, there's 2 problems. First of all, if P1 already got the CPU because he came first, then it's too late. He's already in the system. But let's say we had in our queue 100 processes. So we'll just take, so it's true the first one to come, but now we have a queue of a lot of processes. So we'll just take the shortest ones first. So that's so like you said, first of all, the shortest job first is going to be ideal if we want to minimize wait time, because we're going to get lots of people through with very little wait time. And the one guy who never had to wait a long time, but it's only one guy, he won't ruin our averages so much, because we'll have so many that went through quickly. It's like the doctor who would take all the patients in 1 second. But of course, as you already pointed out, what's the problem with that?
Whoever gets P1.
Exactly. The guy who has a 2-hour procedure, the doctor may end up keeping him waiting until 5 o'clock and then say, sorry, I gotta go to sleep now. And then that guy has to wait all another days. So what we call that problem is called, as a special name for it, we call it starvation. We've starved him because he doesn't get his resources. He doesn't get it's not food in this case that we're starving of CPU time. So anyway, we associate each process with the length of its next CPU burst. We use these lengths to schedule the process with the shortest time. There's just many problems here. One problem is, how are we in the world going to know the next CPU time? Secondly, we're going to have a starvation problem. Now, let me just finish before the question. SJF is optimal. It gives the minimum average wait time for a given set of processes. It's optimal in the sense it's always gonna be the best, because if you could always put the short ones first, your wait time and even your throughput will be the best. In any given period of time, you'll get the most processes through. It's good to keep that guy who's gonna jam up our whole system. We'd rather never treat him. If a doctor wants to show his manager that how many patients he can handle, he'd rather never handle that patient. So we don't care that he's starved. If we're talking about optimization of our criteria like wait time or throughput, well, optimal is that we keep that guy waiting as long as possible. So it gives the minimum average wait time for a given set of processes, also not just wait time, also throughput, gives maximum. The difficulty is knowing the length of the next CPU. How in the world are we gonna actually know that? We could ask the user, we could ask the process, process could report what its projected things are, but that's also kind of silly idea. How are you gonna do that? So SJF is theoretically optimal. It suffers from these two problems, basically. One is starvation, and the other is that we don't have a way of knowing the CPU. So let's just, after we've explained those things, let's look at an example. So here we have 4 processes come at the same time. We know their burst times it's given to us from on high, and these are their burst times. So who's going to go first? P4, the shortest job first. So P4. Who's going to go second? P1. There he is. P3 and P2 is the longest, so he'll be last. And then we calculate the wait time. Well, what is the 3? The 3 is for P1. P1 waited 3. 16 is for P2. He didn't start till 16. This is for P3, he's till 9. And lucky P4 was only 0. We add it together, divided by the number of processes, and we get 7. The average wait time is 7.
Question,
Yes.
burst time and turnaround time are the same thing?
No, burst time is how long I want the CPU. Turnaround time is a measure of how we evaluate an algorithm. Turnaround time says how many processes can we turn around, can we put through the system in a given amount of time.
Thank you.
Okay, so like we said, we have a problem of calculating the next CPU burst. So what is the best predictor of the next CPU burst? The previous CPU burst. And what's the next best measure of the next CPU burst?
That one.
The previous, the earlier one. The further history is also a good predictor, not as good as the most recent. Recent history is usually the best predictor. So,
What about the wait time?
no, we're not going to use the wait time to predict burst time. I mean, that would be, there is an idea like that. It's not exactly what you're saying, but there is an idea to deal with starvation, the problem of starvation, which is that if many people have been going in front of me at the doctor's office for 1 second and I need a 2-hour procedure, as my wait time increases, we'll use that to sort of mitigate the way we evaluate my CPU needs.
Some sort of
So
weighting system.
we'll give me a higher priority because many people have passed me or I've waited a long time. So there's a term for that. That's called aging. To deal with the problem of starvation, we age the process. We say, you've been waiting, your age is going higher and higher. That means your priority is getting higher and higher. And at a certain point, you'll get service just because you've been waiting even though you're long. And there is an idea like that. But that's what we're talking about, something different now. We're talking about predicting the next CPU burst based on the previous CPU burst.
We assume that in the exact second that the previous ended, we're starting with the next one.
Yeah, we're gonna ignore the dispatch latency. We're ignoring the dispatch latency. We're assuming that one starts and the one ends, the next one starts. But it's true. All of these examples are really technically wrong because there's also a dispatch latency, which we didn't talk about. We talked about, but we didn't enter into our calculation because it's constant. Actually, we'll see that in another algorithm, the shortest remaining time first, it would be logical to include the dispatch latency there. we'll see that algorithm, and I'll mention that again. So we can estimate it. Should be similar to the previous one, then pick the process with the shortest predicted next CPU. We're gonna make a lot of predictions. Can be done by using the length of the previous CPU years using exponential averaging. So here's this little formula. And what this formula says, it's a little bit confusing, but I'll explain it part by part. Excuse me if I don't say the names correctly of the Greek letters here, but I think this is a tau. And what this is saying is our prediction at time n, our prediction. Wait, n equals 1, is this n?
It's supposed to be n plus one.
Yeah, I think there's a mistake there, yeah, exactly.
I think the first one's supposed to be n plus one. I think the first one's the second one's a mistake.
No.
This is n,
No. It's n plus one. It's supposed to be n plus
Why?
this is n minus 1.
No, it's N,
No.
because the tau is,
one. I think the t and tau are supposed to be the same.
Is 10 0 then?
Yeah.
This should be t n plus 1.
the type
No,
of
it's T.
tau N equals one should be N plus one.
That's it.
What did I do? Wait a second.
Yeah.
Well, I'll just explain to you what it's supposed to be. I'll explain to you what it's supposed to be.
Yeah.
First of all, the alpha, this is saying the prediction, this is saying the current burst.
Yeah.
This is the most recent burst. Let's say the most recent burst was 10. So that's the alpha times t. T of n it really should be n equals whatever of a certain burst. The burst that let's say we're on burst 0. So burst 0's time was, let's say, 10. And this tau is the tau that I previously calculated.
Or would that be use of price? Oh, it's instead of going back all the way to all the times, you just take the tau.
The tau that I previously calculated, exactly. So in other words, if let's say the first time I have a priori, I just decide that my prediction is always 10 microseconds. So this will be let's say alpha is 50%. Alpha is set to a half. So I'll say it like this: half of my prediction for the next burst will be based on the current burst. That's alpha times tau of n, of t of n. And then 1 minus alpha, which if it's 50%, will also be 50%, if alpha is 50%. So 50% of it will be times the prediction that I previously had, which if I'm starting off at 10 is 10. If I'm just a priori saying that the starting point is 10, then it's 10 times a half, so that's 5. And then let's say my current burst was 7. So it'll be half of 7, 3.5. So 3.5 plus 5 is 8, because we'll go round up. Sorry, it's 9. 3.5 is plus 5 is 8.5. But we'll round up to 9, because you can't have a burst, like we're going to keep it in integer units. So our next prediction is 9 in that system. Now our next prediction is 9. And let's say we predicted 9 over here, but let's say, I mean, we'll do an example, but I think I have an example here. Do I have an example? Yeah, here's an example. So again, let me just explain. T of n is the actual length of the nth CPU burst. Tau of n plus 1 is the predicted value for the next one. For the next CPU burst. So this should really be, I mean, whatever, you could write it different ways. This should really be tau n plus 1. And this should be tau n. And this should be burst n. This should be plus 1 instead of equals 1. It should be t of n plus 1. That's how we have to fix it. It should be tau n plus 1. Whereas the next one is equal to the previous one times some percent plus the previous prediction plus the previous reality times some percent. This is called, we call this he called this an exponential averaging, whatever, okay. It's also a kind of weighted average, where the weight is the alpha. And the alpha could be half, but that makes life easier.
Oh,
We could weight it in different ways. We could say. If the alpha is, let's say. 80%, 0.8, what would that mean? It would mean we'd give a lot of weight to what?
Current,
The current prediction, and we give very little weight to all previous. Events, okay. But, okay, so here is a preemptive version of the shortest. Remaining time is shortest, preemptive version called shortest remaining time, because we previously called this shortest job first. Now we're gonna say shortest remaining time first. What do we mean by preemptive? Preemptive, we mean, let's say that a process comes in and he got in because he was the only one there. So he got in, he was 100. And then comes in somebody else who's only 5. So we immediately preempt him and say, sorry, we're gonna stop you in the middle. We'll give you back, let's say you worked already for 2 seconds, so we'll give you 99 seconds later, but in the meantime, somebody came in who's 5, and 5 is less than your remaining time, which is 98. So 5 will go first. That's what we call it, shortest remaining time first. His original time was 100. After 2 seconds or 2 microseconds, another process came in who's only 5. So we preempt him, and his 98 seconds will do, his 98 microseconds will do later. And we'll let this guy for 5 go, because 5 is less than 98. If he had already run, let's say it was 100, and he had already run for 96 seconds, and he only had 4 remaining left, and then a 5 came in, we wouldn't preempt, because 5 is, even though it's shorter than 100, but it's not shorter than what's remaining, which is only 4. So that would be a version which is called shortest remaining time.
So how does the computer know that each cycle is like independent, that you can split it into different times, and then where's all the data being saved of everything that you already did before?
Oh, you mean where, you're asking, I think you're asking is where do I keep track of these towels and all these numbers? So I'd have to have special hardware for it. I'd have to have special hardware for it, because I couldn't just use, if I would use like a regular program to calculate it then it would take time. And all that time would be wasting all the advantages I'm trying to get. So it has to be stored in special hardware. Because if it's hardware is always faster. You can't just put this algorithm on any operating system. You have to have a computer built to handle this algorithm. And therefore it's kind of theoretical. And that's why we're studying it in a university course, because it's a theoretical subject that is worthy of being universityized. So wait a second. Now here's an example. I think I brought. Here's an example where we see the guess. Now notice that there's a 10 in the guess row. There's a 10. It says tau of I. All right. Well, I brought a 10. Where did you get 10? Oh, here. There it is. So the original tau is 10. So what is our prediction going to be? Our prediction is going to be 10. So that's our prediction. What's our next prediction going to be? Well, in reality, what happened was the actual burst was 6. So we're going to do 6 plus 10. And we're going to do 50% of each of them. So it's really going to be 3 plus 5. And it's going to be 8. So our next prediction is, maybe I'll erase this. Hasn't been erased probably in like a month. I always think they should have a person whose job it is to erase these things. But this is going to be 5. Half of this and half of this is going to equal 8. And that's our next prediction. That's our 8 over here. Our 8 here is our next prediction. Now our prediction is 8. So in reality, so our next prediction is 8, and that's this point. Now our next, our next prediction, sorry, our prediction is 8, but the reality was 4. So our rule is we're going to take half of this, which is 4, and half of this, which is 2, and we're going to say 4 and 2 is 6, and that's our next prediction. And that's what you see here, our next prediction is 6. Then, but 6, where's our next prediction? I always get lost here. Here is our 6. But now the actual reality was 6. So what's our prediction gonna be? 3 plus 3 is gonna give us another 6. So our next prediction is 6 again.
What is the prediction useful? Like what? Are we
But the actual reality was 4. The actual reality was 4. Wait a second, wait a minute. The actual reality was 4. Why are we making these predictions?
Yeah.
We're making these predictions so that we can compare 2 different programs, 2 different processes, and decide which one is shorter, so we can schedule the shorter one first.
That's the actual decision that we're gonna be making. It's not gonna be the greedy one, it's gonna be the. Or is
We're
it
doing
gonna be-
shortest job first. In order to do shortest job first, we need to know who is the shortest job. So we have to be able to predict the future. We're not given from on high numbers, the operating system needs to know what's the length of the next burst of a particular process.
So this
You
is
can't
short-
know it by anything other than history.
So within each process, this is stored.
So in each process, in each process, immediately when the process finishes running.
Yeah.
We then know his length, finishes his burst, we then know the length. And then we can calculate the prediction for the next time.
Isn't it like the hardware has to keep track of processes?
Yes, you'll have to have registers for as many processes as you can handle. If you can handle 100 processes, you need 100 registers. Yeah, you'll need some kind of yes. Yes, you'll need hardware.
It's not just theoretical, it's unrealistic.
It's probably unrealistic. Okay, but it's something to study. So now our next prediction was 6, and that was this dot over here. But the reality was 4. So it's 2 plus 3 is how much? 5. Our next prediction is over here, 5. That's our next prediction. But the reality was way up here, 13. So, right, the reality was 13. This is the reality. This is the black line represents the reality. So now we take half of 13, which is 7, I guess, and half of, well, actually, it's really 6, let's say it's 6.5, and half of this is 2.5, and 6.5 and 2.5 is 9. So our next prediction is 9, and that's this point over here. And the reality wasn't 9, it was 13 again over here. So now we take 13 and 9, half of 13 is 6.5, half of 9 is 4.5, 11. So our next prediction is 11, and that's this point here. And you see what's basically going on here is that as we were off, right? Our first prediction was off. It was low. So we quickly came down and got near the right point. Then as it jumped way up to 13, we quickly went up. But we don't get there immediately. We don't really run to 13. We get there slowly. If our alpha would be a larger number, like instead of 0.5, be 0.8, then we would get when the change happened, we would react faster. We would react to it faster. But it's not necessarily good to react fast to a change because it could be an anomaly. It could be a change that just happened one time, and we don't necessarily want to let that skew our next prediction. What?
Who decides the alpha?
The designer of the operating system.
It's not like something that we could hypothetically move it to change. Like in the middle or.
You could change it from day to day, but you couldn't change it. You couldn't change it from program to program. You got to use the same
Because it's like,
alpha.
wow, it seems to be off by a lot, things are going really good.
Exactly. So you'll run 1,000 test programs, and you'll see, and you'll change the alpha, and you'll see which version of alpha gave you the best results on your 1,000 test runs. And you'll say, oh, I've scientifically shown that given a large sample, this is the ideal alpha.
But isn't it on the hardware? How can you change it quickly?
Because you'd run the test program on you're saying it's in the hardware, yeah, but it could be it's a register. Hardware doesn't mean hardware could be a register, doesn't mean it's not writable.
Yeah.
Okay, so here we just basically did what this is just showing you what we did, and it's showing you how you calculate. How the next here says t, here it says tau and n plus one, like it should be. Here it was, here was a mistake, I don't know why. I've seen this slide many times, I think it's been fixed and then unfixed, anyway. Here you see it's tau n plus one equals alpha times t. Plus one minus alpha times t of n, t of n minus one, or of n minus one, it just keeps going, fine. Since both alpha and one minus alpha are less than or equal to one, each successive term has less and less weight than its predecessor.
What does, on that slide, recent history does not count, that means like previous times?
Oh, yeah, I'm sorry, I skipped the beginning of the slide. Thank you. The alpha equals 0, as if alpha would be 0. Then if we go back to our formula, this element would disappear. And we would just have 1 times the previous guess. So it would always, if we would started our guess at 10, our guess would never change. And if alpha would be 1, then we would only look, then what would happen? Then 1 minus 1 is 0, then all old history would disappear, and only the previous 1 time would make count. So if alpha is 0, recent history doesn't count, only the old history, only the first prediction. If alpha is 1, then only the actual last CPU burst counts.
Thank you.
That's just a theoretical result of the formula. Obviously, we would never probably have alpha be 0 or 1, but we could move it around, like I said. Preemptive version of shortest, so shortest remaining time first is what I explained to you. It's a preemptive version of shortest job next. Whenever a new process arrives in the ready queue, the decision on which process to schedule next is redone. So this is preemptive. If we talk about a preemptive, we're gonna check every time a new process comes. We have to start checking what's his remaining time. How much is the guy? What's his predicted time? How much is the remaining time of the one that's currently there? Based on our prediction, and we made preemptive. The shortest remaining time. Is shortest remaining time more optimal than shortest job next? It's funny, they're just using different terms here. Shortest job next. We called it SJF. Short SJF, we call it shortest job first. But here we're calling it shortest job next. It's the same thing, basically. Shortest job, because it's not first, it's next. The next job will be the shortest job. So is shortest remaining time more optimal than shortest job next in terms of the minimum average waiting time for a given set process? Is it more optimal? We already said that shortest job first is optimal. Could it be that this preemption is more optimal?
No?
Well, in what case would it be better?
Which one? Depends which one's shorter. Remaining time could just.
Well, we're asking, is shortest remaining time better? And you're saying it depends, which means you'd say it could be.
Yeah.
So when could it be better than shortest job next and shortest remaining time? Shortest
If the remaining time just, when you sum it up, it's less than.
but mathematically, you have to think of a case where you have to work out a case where you have to come up with a list of predicted times and show that by preempting, I make it go faster than. Why not? Well, the answer really is no, it won't be better than optimal. It could be worse, but it won't be better. Yeah. Anyway, you can work out the answer to this question by an example. Try coming up with some examples. See if the preemption will help. What will the preemption really help us with? Well, it does make sense that it should help, because we got this big guy who came in just because he was the only one there. Actually, it should make sense that it would be better, because we have this big guy there and we're gonna pull him out and put somebody else in. So we'll get more people, the wait time of that guy will be small. So it should be better. It should be in a sense more optimal. But it depends how you think about optimal, right? Exactly. I think it depends how you think about optimal. Because usually when we talk about optimal, we talked about they're all coming at the same time. If they're all coming at the same time, then they'll never put the big guy in. Okay. example of shortest remaining time first. So here's an example. And what do we say? Well, the arrival time is different here, okay? So we have no choice but to put P1 in at first, right? Because he's the only one in the queue. P1 is arrival time at 0. At time 0, we only have one process. So P1 goes in. But his burst time prediction is 8. So now comes along at time 1, P2. So P2 is going to preempt him. And he only got work for 1 second. Because he's got 7 more to go, and P2 has only got 4 more to go. So P2 is going to go for his whole 4, because 4 is actually the least number here. So for sure, P2 is going to go his whole 4 till 5. Now, by time 5, everybody's in. Who is going to go next? Well, could be P1, but he's 7. Because he used to be 8, but now he's 7. It could be P3, but he's 9. So it should be P4, who's 5. And he'll just keep going. He's 10. And then comes P1 again, because, well, wait a second. Why P1?
Because seven left versus 9.
Thank you. He's 7 left versus P2, versus P3. It's very confusing because these numbers are 1 different. But yeah, P3 is 9, so P1 goes first, and we get the average wait time. So what's the average wait time? Well, this should be for process 1. He waited 10. That's a little weird the way they wrote this here. He waited 10, but it's 1 minus because he didn't wait the first minute, so it's really 9. And it's from 1 to 9 is 9. From 1 to 10 is 9. So he wrote 10 minus 1. And now it's true that P2 started only at 1, but he only arrived at 1. So it's 1 minus 1 or 0. Now, what about P3? P3 started at 17, but he didn't wait the whole 17 because he only came at time 2. So 17 minus 2. And similarly, P4, he came at time 3, but he only started at time 5. So it's 5 minus 3, which is 2. We add those all up, divide by 4, and we get 6.5. I don't know if I did it here. Let's do something. This is great. I already skipped way too much. Yeah, let's do this example again. Let's use the board that we have here. Let's do this example again with and not do shortest remaining time. Let's just do shortest job first. So at time 0, it'll be P1. So at 0, it'll be P1, and we're not going to interrupt him. So he's going to go till time 8. By the way, it's very confusing. You can think, well, maybe it should be 7, 0 to. But it should. What number should I write there?
8.
8. 8, because 8's when because it's here. Let's look at this. 0, 0, 1, 2, 3, 4, 5, 6, 7, 8. So this is 1 unit, 2, 3, 4, 5, 6, 7, 8. Wait. 1, 2, 3, 4, 5, 6, 7. Oh, I drew an extra line. Yeah. So 1, 2, 3, 4, 5, 6, 7, 8. 8 units. We got from 0 to 8, and now at 8 we can put somebody else. Who are we going to put at 8? Well, who are we going to put at 8? Everybody's arrived. So who are we going to put in? I say P2 too. So P2, and he's going to go for 4, so that's 12. And then we're going to put in P4, and he's going to go for 5, so that's 17. And then who?
P3.
P3. P3. So actually, what is our wait time? Well, for P1, it's 0. For P2, it's 8 minus 1 or 7. for P
Four.
for 3, we go to 3, we go in the order that they are.
Correct.
For P 3, it's 17, but it's -2, so it's 15. And for P 4, it's 12, but P 4 came at 3, so that's 9. So 9 at 16 and 17 is 31 divided by 4 is 7 3/4, something like that. Is that right? 31 divided by 4.
No, it's there.
It's 31 divided by 4. Am I
Yeah,
right?
yeah.
Good. 7 3/4. So
Better?
7 3/4 is worse.
Worse. Oh,
Is worse. So it is worse. So it is more optimal. It is more optimal, but again, it depends on how you define it, because when we were saying optimal, what we meant was optimal, assuming they all come at the same time. And then they're the same, actually, if they all come at the same time. There's no preemption. When they all come at the same time, there's no preemption. So it could be more optimal, actually. In a sense, it is more optional. Could it be worse?
can we,
Well, it really depends. What does it depend on?
the definition of optimal.
No, it depends on, the dispatch latency. Remember we talked about dispatch latency? If we're gonna start preempting somebody all the time, and that's gonna cause us to have a dispatch latency, context switch overhead, that time will start to become relevant. Once we start to interrupt somebody, let's say we have one long process, and he keeps trying to run, and just as he runs, somebody else comes in, he got 1 second in, and then we stopped it, another second in, and we stopped it. All those context switches could start adding up to be problematic. So it could be suboptimal.
Just to reiterate, when do we interrupt? Like when we interrupted at T1, T equals 1? We interrupted.
We
T1
interrupt,
at T2.
it went because P2 arrived to the system at time 1. And we looked at his predicted burst, and his predicted burst was 4, which is less than the remaining time of P1's prediction, which is 8, which means 8 minus 1 is 7. So 4 is less than 7, so we preempted P1.
So basically at every time unit, we would be checking all of the
No, not every time unit, at every time a new process enters the ready queue.
got it.
Anytime a new process comes to the ready queue, we have to say, well, what's his prediction? Should that cause preemption?
Thank you.
And that's back to what we said before. That is exactly what we said way back here. When we said if we go from running to ready, well, that must have been a preemption. Why would we stop him in the middle of his running? He wants to keep going.
That's what.
It must have been, we preempted him. That's what we said. We said when you go from running to ready, then that means there was preemption.
Thank you.
Okay, so we're back over here. Shortest remaining job. Priority, just make sure we did this. Yeah, we did this. Okay. Priority scheduling, priority number integer is associated with each process. So here we just say, if you have a higher priority and you're a VIP and you're in the queue, you get serviced first. We don't care how long you've been there or anything. The CPU is allocated to the process of the highest priority. Usually the smallest number is the highest priority. So usually we say like 0 is the highest priority or 1 is the highest priority. And it could be non-preemptive or preemptive, because we could say, well, you'll be the next one up, but we're not going to preempt somebody. Or we could say, no, we are going to preempt somebody. Shortest job first is priority scheduling, where the priority is the inverse of the predicted next CPU burst. In other words, the lowest, the priority is higher if your next burst is lower. That's why we say inverse. Your priority will be higher if your next inverse, if you think about it, shortest job first is a kind of priority. The problem is starvation, which we mentioned before. Starvation means if the high priority jobs keep coming and the low priority jobs never get serviced, they will be not serviced, and so that's called starvation. The solution is aging. As time progresses, you increase the priority of the process. You give him a higher. That's one solution. You change the priority. His priority keeps getting higher priority. Example of priority scheduling. This is kind of trivial, really, but let's just to understand it. We have a bunch of processes come, and we don't have their actually it's less interesting because we don't have any arrival time here given.
Mhm.
Right, you gotta be flexible, you gotta notice that we have a priority given, we don't have an arrival time, so what do we assume when we have no arrival time? Same time. What do we assume about if two people have the same priority? Well, we don't have that in this case, but if two processes would have the same priority and the same arrival time, which one will go first? What? No, I said the same priority and the same arrival time, which one will go first? The number, the ID number lowest, the lowest in the ID number.
Did we say that means that came first then?
What?
Did we just say that that means it came first?
They came, oh, you're saying, but we're not keeping, the arrival time, they both came at the same time, but we're not doing first come, first serve. We don't know who came first. We just know they came at time 0. We don't know who came first. We're not keeping track of that. All we're keeping track of is their priority. So we have, with tiebreaker is always by the ID number.
What's considered a high priority number, is that 1 or 5?
1.
Thank you.
So here, because 1 is a high priority, P2 goes first, then goes P5, then go, because he's 2, and etc. So this is trivial. This is just giving you just do it according to the priority. It would be more interesting if you had combined it with arrival time and preemption. Then you would see more movement going on, right? If you would have an arrival time and they came at different times, and then you had preemption, so then somebody who was a low priority went first because he was the only one there. And then he got it preempted because of somebody else coming. That could be more interesting. Round robin. So round robin is what we've been mentioning all along, and it's just, we called it the name time sharing, but now we're calling it the name round robin. Why? Because you're going around all the processes in a circle, and you come back to the same process. Everyone gets their slotted time in a circle. So that's why I call it round robin, but it's also with time slots. So whenever you think of round robin, whenever you see RR, don't think reading railroad.
Railroad, yeah.
Don't think a railroad, think time slice. Each process gets a small unit of CPU time called the time quantum, right? You know that the word quantum means amount. Really, or a small amount. Like quantity. Quantum is like from the word quantity. A quantum leap means a small leap. Really. It's a leap. Discrete leap. It's usually, so we're gonna say here that the amount of time is usually 10 to 100 milliseconds. You do not have to remember that, but the point is just to give you an idea of what it should be. It's, let's say 10 milliseconds, 100 milliseconds. A millisecond, which is bigger, by the way, a millisecond or a microsecond? Millisecond is bigger than a microsecond. A microsecond is a million. Power of 10 to the 3.
What is it?
Milli is from the Latin for 1,000. Millisecond.
Is it really 10 to the 2, -2, and then
No, we're in base 10 here. So a millisecond is 10
to the
10 to the 3rd. A micro is 10 to the 6th, and a nano is 10 to the 9th. A nanosecond. But we're talking here about 10 milliseconds is a lot of time. That's a lot. So for a computer, 100 milliseconds is a lot of time. Although we're not gonna, yeah. So in reality, it's a lot of time because there's a lot of microseconds in. How many microseconds are there in 100 milliseconds? No, to how many? I don't know how to say microseconds, but how many nanoseconds? 100 million. 100 million nanoseconds. We're gonna stop for a minute. Okay. So pause the recording. Resume recording. Okay, we're back. Round robin. Each process gets a small unit of CPU time, which we call a quantum. We said how much time that is. After this time has elapsed, the process is preempted. That's our favorite word for today. And added to the end of the ready queue. In other words, he preempted because his time is up, but not because he wanted to go to I/O. So we're not going to put him in the waiting queue. We're going to put him in the ready queue. He's ready to get the CPU. He's not waiting for I/O. Now, an important point to mention here, and I'll mention it maybe more than once, but I'll mention it at least once, and that is that if there's an I/O event before his quantum, has finished. We also, we don't interrupt him, he interrupted himself, he went to do IO. So we also give the CPU to somebody else. So if his 100 milliseconds has not elapsed, let's say 50 milliseconds has elapsed, and now he wants to read a file, we'll give the CPU to somebody else, and when he comes back, and when he finishes getting his IO, he'll go back to the ready queue. And he'll be just like any other process, and he'll get 100 milliseconds. So it's a maximum that you get, not you don't get that amount no matter what.
The program that replaced him, like halfway through, let's say, is that considered their quantum or?
No. The program that replaces it gets a whole full quantum of 100 milliseconds, let's say.
Let's say one process finishes halfway through, and then it goes to an IO event.
And then some other process goes to the CPU, he'll get a full 100 milliseconds.
Oh, okay, we just end it early.
Yeah, we ended early. Exactly, the same thing if he terminates. If he terminates early, we're not gonna just wait around, we're gonna immediately schedule somebody else. If there are n processes in the ready queue and the time quantum is q, then each process gets 1/n. And the time quantum 1/n of the CPU time. Obviously, they're gonna divide it up evenly. But they're in chunks of at most, that's the key word there, at most q units. In other words, at most you get 100, and we're dividing up all the CPU equally, and everybody gets at most one. They get their proportion of the CPU time, but in chunks of 100 of whatever the time slice is. No process waits more than n minus 1 times q. Q being the number of, in other words, the quantum, and n being the number of processes. Right? There are 100 processes, the maximum time I'll wait is 99 processes, n minus 1. I'm not gonna wait for myself. The timer interrupts every quantum to schedule the next process. So there's a timer. Every computer has a clock, and we set basically the minute the CPU schedules you, puts you into the minute the operating system puts you into the CPU, it immediately starts a timer. And when that timer rings, after 100 milliseconds, an interrupt happens. So he sets the stage for the interrupt. The operating system puts on an interrupt that will be in a certain amount of time. We call it an alarm or whatever you want to call it, timer. Performance. If Q is very large, here's an interesting theory. If Q is an observation, I should say. If Q is very large, which means the quantum is very large. Let's say the quantum is so big that almost nobody ever uses it before they go to IO. Nobody ever fills. They give them such a big number. We give them 200 milliseconds. So now the processes never need that much. They always finish early. Well, then we have just a regular first come first serve. We're just whoever's in the queue, we go in order. We're not, because we never did a preemption. So if the queue is very large, if the queue is very small, well, this is what we mentioned before, the queue, that's not so good if it's very small, because it should be large with respect to the time of the context switch, what we call the dispatch time, the dispatch latency. In other words, the queue can't be, it should be 100 times bigger than the dispatch latency, for example. Otherwise, the overhead is too high. Example with a quantum of 4. So here we have P1 comes in. And they're all coming at the same time, but P1 will get service first. We don't care about we're not shortest job first. We're not even first come, first serve. We're just, well, we are kind of, we are kind of first come, first serve. In other words, we have to have some way.
I mean, they're all coming at the same time. So
They're all coming at the same time, but so then, and even if we say that we have to say that P1 came first at that time. Could say they came all exactly at the same time, and then the order is by the number. In any case, I'm just saying that inherent with the round robin is a kind of first come, first serve, because we just said that. We said if the quantum is very large, then it is first come, first serve. So that means, so first come, first serve is kind of like what's going on behind the scenes always.
well, why is it 4 in the first one and then there's 3?
Oh, because P2 is
Only 3.
only needs 3, doesn't need 4. The quantum is 4. His desire is less than we a lot.
And they just wrote it without any other criteria, just in the order that they came.
I don't understand. P
Meaning-
one gets interrupted after 4.
If P2
P
was
three
5,
finishes, he terminates.
if P2 was 5,
What?
if P2 was 5,
Then he would be, then he would appear again over here.
okay, but it doesn't choose P2 again before P1 because it's gonna be done with it.
No, 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 no.
This is the only criteria.
The only criteria we have is the order, which is first come, first serve, and then the quantity. So we start off with P1, then we go to P2, he finishes, P3 he finishes. Now we go to P1, now. It's a little bit weird, it's a little bit confusing to me, this line here, because. You know, an interrupt will get called because the operating system doesn't know there's nobody else in the queue. And maybe somebody will come to the queue exactly at that moment 14. But I assume that if the interrupt is called and then the operating system sees that the queue is empty, which it is, he's not going to dispatch this guy. He's not gonna like take him out and put him back in. That would be, he would be smart enough to realize the queue is empty. I'm just gonna leave him in. So this line is just indicating that a timer will interrupt at that point, but then it'll immediately continue. It won't, nothing will really happen. Typically, we have a better, higher average turnaround time than shortest job first. Well, wait, we said shortest job first is optimal. We said it's optimal, so why is this, but it's optimal in the sense, I guess, of wait time, for wait time is optimal. But here he's saying the higher average turnaround time.
Turnaround time is bad, right?
Right, we don't want, exactly. We have higher average turnaround time, that's bad. That's good, okay, so that's bad, and therefore it is less optimal. But better response time. Why do we say better response time? Remember that was another criteria we talked about? Response time is when do I get a response from the computer? Well, if I would have let P1 go for 24 seconds, then P2 wouldn't have gotten a response right away. Now he gets a response very quickly. So we're gonna have, so generally we're gonna have a higher turnaround time, which is bad, but we'll have better response time. Q should be large enough to compared to the context switch. We said that 3 times.
You said large turnaround time?
Well, a large turnaround time is bad, right? Because it means how long does it take for the average for one process to get finished? It'll take longer for him. Why? Because he's constantly getting interrupted. He doesn't get his time. What I was thinking is throughput. What about throughput? Throughput should be, we would like to have a throughput to be high. So here, what would we say about throughput? Well, it should be lower than shortest job first. Shortest job first is optimal, really. So it's going to be worse than, but it'll be still a pretty good throughput because the short jobs will get through. It's kind of like if I had imagine if I had a grocery store and I had a checkout system like this, that you only have one checkout line, but everybody gets 10 items to go through at a time. So if you have 100 items, you'll have to get 10 items paid and then go back to the end of the line. And if somebody was behind you with only 2 items, he'll get through. So we'll keep, but you'll eventually get through because you'll keep getting your 10 items. Eventually you'll get 10 times, you'll get 100 items through. But we'll also get the people who are short. So we won't have starvation. And we will get a fairly good, throughput. Let's say, well, a high throughput because those short people will get through. But it won't be as good as shortest job first. Because shortest job first says just push the old guy, push the guy with a lot of groceries to the back and just let everybody go in front of him. Then we're gonna obviously get better throughput. Q should be large compared to the context switch. We said that, right? The context switch is our overhead. We want the overhead to be small relatively. Q usually is 10 to 100 milliseconds. Context switch is usually less than 10. No, nanoseconds. I think that's picosecond. Isn't that nano?
That's in the unit.
I don't know.
Oh. U is nano, yeah.
It's actually a Greek letter.
Yeah, it's a Greek letter, U or something. Yeah, that's nanoseconds.
100 milliseconds seems like a really long time for.
It is.
Even though you didn't notice on your computer.
No, because it means in a tenth of a second. It's still pretty fast. You're right, well, if it would be 10 milliseconds, it'd be a hundredth of a second, you wouldn't notice it. Okay, time, quantum, and context switch. So. If the process time is 10. And if the quantum is 12, then how many context switches do we have? 0. If the process is 10 and the quantum is only 6, then we're gonna have 1.
You just divide the number by the other one.
Right, if the quantum is only 1 and we have 10, then we're gonna have 9 context switches. Cause not 10, 9.
-1.
The time quantum, so. This is the average turnaround time, you could calculate this, but we're not gonna calculate it, but this is saying the average turnaround time, which we want to be high or low. Low, we want it to be low. So we want it to be low, and if the quantum is let's say 1, it'll be 11. An interesting thing is that if you make the quantum bigger, what would you expect? What would you expect? How should this graph really look?
Huh?
How should this graph really look? Should it be like this or should it be a straight line? I mean, not a flat line, but a straight line. If it would be a straight line, which way should it go, would you say? The average turnaround time, should we get better turnaround time? Turnaround time means how long it takes for a program to finish.
Technically, she gets.
Well, if it would be throughput,
Then it would go up.
then it would go up because we would get more throughput. Wait, we know. If our quantum was infinity, then our throughput would be, then it would be bad. We have bad throughput.
Yeah.
So it should go down.
Yeah.
We want it to be small, but if it's turnaround time, the amount of time, so. If it's small, if the quantum is very small, then the turnaround time for us, even for a small program, let's say only 10, but if the quantum is only 1, then he has to wait for everybody to go through many times. So the turnaround time, the average length, he has to end up waiting for everybody in the list. So the truth is a small quantum and it is not so great. What do we want? We want the average turnaround time to be low. So actually, we want a larger, here it's saying that as the quantum is bigger, like 6 or 7, it's better. If it's 5, it's not so good. It should really go down. It should in general go down like this. Because to give her a bigger amount of time, but if it gets to be too big, then I don't get service. So it is kind of goes up and down like this. It makes sense. Not so clear, and it'll depend on, this is for a particular set of programs. This graph is not always true. This is a graph for a particular set of programs for this set, for this set of programs. You could calculate 80% of the CPU burst. Here's a rule of thumb. 80% of the CPU burst should be shorter than the quantum. In other words, the quantum should be large enough that 80% of the jobs finish in one quantum. We don't have to break when they get out of the queue. Once they get serviced, they're done. I don't mean they've terminated. I mean, they're done, they went to IO. 80% of the time, because we don't want this poor short guy to have to come back again. But 20% of the processes are going to be the larger ones, and they'll take more time. We're assuming that like the top 20% longest are going to should have to hang around and should be suffering a bit. But the 80% that are short, though, shorter 80% should be finished in one quantum. Okay, now we can have, if we understood all those things, we can have what's called a multi-level feedback queue or a multi-level queue. A multi-level queue, sometimes I call it a multi-level feedback queue, means basically that we have two queues. Two queues. For example, if you think about a supermarket example, instead of having one checkout person, I can have two checkout persons. And I can say like this. Everybody who wants to buy anything has to first go to checkout person number 1. And there you buy 10 items or less. If you have more, if you still have more, then you go to the second queue and there you can buy 100 items or less. Those are two quantums, a quantum of 10 and a quantum of 100. So what do I get by this? Everybody gets their 10 servicings. But if that wasn't enough for you, then we'll put you in another line where you get a larger queue. Now, the difference is usually we don't have two CPUs, we have one CPU. So how do you do that with two queues? So what you do is you say like this, you only have one checkout person, but you have two lines. And what the checkout person does is they say, if there's people in the short line, then I'll stay there. And I'll just keep on servicing the people with 10. Now, eventually, all the short people will get through. And all the longer people will start getting pushed off to the side into that other queue. And now when finally I finished servicing everybody in the short queue, now the checkout person will go into the long people, do the bigger carts, the bigger shopping carts, and we'll start handling those. If somebody all of a sudden appears in the short queue, well, there's two possibilities. Either you finish the one you're working on, and then you go back to the short queue, or more likely, you immediately stop the one you're working on and go back to the first queue and start servicing 10.
Is that not just the shortest time?
No, because the advantage is that in the shortest time, I had to know ahead of time how much they're gonna use. I had to know, are you 10 or are you 100? So I'll do the 10 first. Here, I don't need to know that. That's the big point. Because calculating that was very complicated. I had to have hardware and I had to do this math to predict it. I had to do a lot of work. So I don't want to have to do that, but I want to get the similar results. So I just say like this, I don't know how much you need, but first come through the short one. And then if you're short, then you're done. So it's ki'ilu, it's as though I have done the shortest jobs first. If you were there, but you're really a long job, then now I figured it out because I did 10 of you. I gave you 10 milliseconds and you weren't finished. So I put you in the other queue. So it's a way of sorting between the two without looking at history. So here, let's see what they write here. Ready queue is partitioned into separate queues. So we have a foreground. So this is just saying we could have some jobs that are foreground and some jobs that are background. In other words, if a job is meant to be done in the background, which means it's not a high priority job, then we can put it in one queue where he's serviced only, where let's say there's always an infinite number of ways of arranging to two queues. I could say another way, I'll do 10 people on this queue and I'll do one on the other queue. 10 people on this queue, one person on the other one. I could do like that, in which case it would just be kind of priority. So I could do that with foreground and background process. I could have a certain process, which is called a background process, a process that generally is run with no real time issues. In other words, I don't care if it takes it an hour. I just run it in the background. Whenever so then it'll get like one. Every other process will get 10 times with the CPU, and he'll only get one. And then the foreground ones will get the 10. That would be one way. Process permanently in a given queue. So that's one idea, is that the process goes either in this queue or in that queue, and the CPU will decide how to go between the two queues. For example, I could have each queue has its own schedule. I could have the foreground queue running round robin every time seconds, and the background queue could be first come, first serve. And then, of course, I'll need an algorithm to decide when I go between the two queues. So I'll need 3 algorithms, right? If I have 2 queues, I need 3 algorithms. Algorithm for each queue, and then an algorithm to decide when I go between the two, when I decide to go that queue or the other queue. That's this line here. Scheduling must be done between the queues. Now, there needs to be an algorithm to decide when to go from one queue and when to go to the other queue. So you could have a fixed priority scheduling. For example, serve all from the foreground, and only then, when the foreground is empty, then go to the background. But then you can have starvation. So you do like I said, you can do 10 processes from the foreground and 1 from the background, then 10 from the foreground. That would be more logical. Time slice. Each queue gets a certain amount of CPU time, which it can schedule amongst its processes. So I give, for example, 80% to the foreground. The foreground is round robin. I can do 80% of the time here, 20% here, 80% here, 20% here. When he's got his 80%, he can divide it up among his processes. Okay, that's one idea. So here you just say, you know, I don't know, low, here's like 5 queues, fine. Not so important, okay. Here's the multi-level feedback, which is what I was talking about before. So a process can move between various queues, aging can be implemented this way. So we're gonna have aging, and that's what I said about aging, which is that. Well, we'll see in the next example. Well, instead of saying that when, you know, I'll say it now. Instead of saying that when you get into the second queue with your 100 items. Let's say that you have, let's say the second queue, the first queue is 10 items, the second queue is 100 items. And you have 200 items. So you get 10 done, now you have 190. Now you go to the second queue, you only get 100. Now where do you go? So we could say, now you get to go back to the 10 queue. So you get a high priority again. You get 10 done, now you have 80 left. And now you go back to the other queue and you get your 80 done. So in other words, you go back and forth between the queues. So a process can move between the various queues, and that way we do aging. That's a kind of aging, because why is it aging? Because you get out of the bad queue. You were in the bad queue, you get service once, but you don't have to go again and do it. Now you get to go to the quicker queue. Multi-level feedback queues scheduled and defined by the following parameters. So we have all these parameters. How many queues? What is the algorithm for each queue? When to upgrade a process from one queue to the next? When to downgrade a process? Method used to determine which queue a process will enter when that process needs service. Which queue should it start with? So here's an example. And this is an example I was thinking of. The example is here. I start off with a quantum of 8. In other words, a time slice of 8. If I can get finished in time slice of 8, I'm finished. If I don't finish, I go to the next queue, and in this queue, everybody gets a quantum of 16. If I finish, I'm done. If I'm not finished, then I go to a final queue, which is, for example, first come, first serve. So that means I'll get it until I finish. That's infinite. That'll be infinite time slice. So there are 3 queues. Scheduling. A new job first enters queue 0, which is service first come, first serve, right? Always we assume first come, first serve when, you know, you say, well, okay, if it's round robin, but like who goes first? So it's first come, first serve. When it gains CPU, the job receives 8 milliseconds. If it doesn't finish 8 milliseconds, it goes to Q1. At Q1, the job is again service first come, first serve and gets 16. If it still doesn't exist, it's preempted and moved to Q2. What's not written here is what to do, like how do you divide the time between these? Right?
Like how do you decide what the quantum is?
Exactly, what the quantum is. No, not what the quantum is. I have this one, anybody in this queue gets 8. But when does the CPU service this queue and when does it service this queue? Can't service all of them at the same time. Because there's only one checkout lady at the supermarket. So is she going to be on this line, this line? So what I said, one solution is to say, as long as there's anybody in this queue, we service this queue, and everybody else has to wait. We only service these when there's nobody. This one only gets serviced when there's nobody here, nobody here. Because remember, the processes will get into this queue eventually. The long processes will all get into this queue. The only problem is a short process can come back and come back and come back and keep me busy over here. So I could have a different algorithm that I'll divide my time, a third, a third, a third. But then this wouldn't really be a first come, first serve. If I say a third of my time I'll be in this queue, a third of my time I'll be in this queue, and a third of my time. So what happens? First come, first serve. After my third is finished, I'm going to stop him and go over here. So it's still first come. When I eventually get back to him, I'll continue with the guy I was dealing with. Right. So you can do it like that.
This is the example you get for a regular multi-level queue. Right, so what makes
This is different from the supermarket, the first one I gave you.
this different?
Because there's no going back. What I said in my one was that there was an exam question like that, and that's why I was thinking of it. There was, where you go from the checkout of 10 to the checkout of 100, and then if you still have more after you go through 100, you go back to the 10. You go back to the 10 and get 10 done, and then if you still need more, you go back to the 100. You keep going back, and then there's the rule that the checkout lady always services whoever's in the 10 first. Until She won't service anybody in the other list until it's empty in the first queue. That was. We like this for exam questions because there's an infinite amount of variety that you could do here.
So what makes this a feedback? As opposed to- what's the feedback?
Yeah, what's the feedback? It's a good question. What?
It's how big the process is.
I think the feedback is that I get information, I get feedback from, well, it could be because it feeds back. In this one, it's not in feeding back. But the way I understood it is that feedback means that you go back into this one. You feed back into the beginning. That could be one idea, that you feed from the end back to the beginning. Another reason, maybe it's, I'm not sure why it's called feedback. Another reason it could be is that you get a certain feedback about the process. You find out about the process, how long it is. So you're developing information from the process. Well, it's not important where it's called.
Right.
Example with IO. So here's an example. An example like a question with IO. What do we mean by that? I mean to say there's a process, its arrival time, then it's CPU need, but then we also mentioned its IO need, and then it's CPU need again. So we're going to think about, in other words, this, what is this going to tell us? This number, this IO is going to tell us when does it come back into the ready queue. Because this number would be very large, let's say 10 over here, then he would never, that 3 wouldn't come back to be on the queue at all for 10 minutes, for 10 units. Fill in the following table for each algorithm showing which process uses the CPU and IO at each second. So here's a table. Well, first come, first serve. Still like this. It's scary. It's a lot of boxes. What it says like this is P1, this is P2. So these 2 rows are P1. These 2 rows are P2. And what you're supposed to do is right here, is he IO? Or is he CPU? Or is he waiting? So for example, in this case, P1. Well, actually, wait a second. There's P1, 2, 3. There's a mistake here because here they're called 0, 1, 2, 3. And here they're called 1, 2, 3, 4. So we should really change this to 1, 2, 3, 4. So, for example, at arrival time is 0, CPU need is 1. So what we'll do is we'll write here at time 0 CPU. Then we'll write here IO. And will we write IO in the next box? Well, it says 2 IO, so yes, IO. Now, so we're definitely going to write CPU, IO, IO. And then in this box, we're not going to necessarily write CPU because there could be another process that gets CPU at that time. Because at time 1, who came into the list?
P1.
P2, we're calling it now.
Oh, come on.
This is P2, we're calling P1, P2. And he came in and he wanted for 2. And then at time 2, P3 came in and he wanted for 3. So what are we gonna see? So let's look at the answer here. We're gonna see CPU, IO, IO, and then P2 comes in and he says, I want CPU for 2. Now, what about P3? P3 actually came in at time 2, but he couldn't get the CPU because it was taken already by P2. So he is here and he wants it for 3. Now, at this point, he has gone to IO, right? But what about P2? P2 is actually interested in the CPU. And so is P4, probably. Let's see P4.
P1 first for the CPU.
So let's go back here. At this point, what are we doing? First come, first serve. So at time 4 or time 3, everybody's in, and it should be first come, first serve. Because at 3, so wait a second. So P3, which is really P4, came in at time 3. So let's go back to our picture. At time 3, well, P1 came in, and also P3 three came in, but P2, right, P3 came in, he got it. Oh, at this point, so who goes first?
Why isn't it before?
Why isn't it P4?
He has come in first. Should he be served first?
No, he didn't, because P1 came back at time 3. P1 wanted the CPU at time 3, and P4 wanted it at time 3. But P1 has got a lower number,
Why does he have a lower number?
because he won, P1. So P1 goes and gets the CPU.
OP.
OP,
Overpowered.
and then when he's finished, is an X here, the X means he's terminated. And then P4 comes in,
What's X is what?
terminated. Anyway, you can look over these solutions, and guess what, we have also for shortest remaining time, shortest, okay. Wait, let me just see, yeah, so let me just. Alright, the last bit is this. I'm not gonna go over those examples, we can do that in the lab. Multiprocessor scheduling. CPU scheduling is more complex when you have multiple CPUs. Right? Imagine all this compounded now by the fact that you have two CPUs and the processes. What if a process was waiting on one CPU and that process is busy? Should he go to the other CPU and see how things are over there? So you can have homogeneous processors within a multiprocessor. You can have asymmetric processing. Only one processor accesses the system data structures, alleviating the need for data sharing.
That's just not using the other processors, isn't it?
No, it means that one processor does a certain kind of work and another processor does a different kind of work. Homogeneous means they all do the same thing. Asymmetric means only one processor is going to be accessing the data. Any data requests will be that processor. Symmetric multiprocessing. Each processor is self-scheduling. All processes are common all processes in common ready queue. So there's one ready queue. This is right. This makes the most sense actually. You have one queue, and whichever processor is available, he'll take it. And then after the time slice finishes, then they'll both go and take people out of the queue. Remember that they're not necessarily in sync because the one process could finish before the time slice finished. And then, so the two processes are not necessarily going to the queue at the same time. Each processor is self-scheduling, all processes in a common ready queue. Or each queue has its own private queue, or each has its own private queue of ready processors. You could have a separate queue for each processor.
Isn't that just asymmetric?
No, I think,
Oh, I guess it's not really. They both are the same queue.
yeah, they're both doing, yeah. No. In the second example, there's a separate queue for each processor. But
Both queues are equal in terms of they do the same things.
yes, they do the same thing, exactly, they're not, exactly, it's homogeneous.
Right.
Currently, that's the most common. Well, either of those two. Symmetric of one type or another. Now, what's the problem with of having one queue and both of them going good? Both. If you think about your class in computer architecture. There's a cache, remember there's a cache? We talked about, we'll talk about this later actually in this course, but the cache has data from a previous run of the program. When the program was running, we didn't necessarily clear out all the cache. When we do a context switch, we don't necessarily wipe the cache clean to start the next process. We might have the cache still have bits of memory for another process, and all we'll do is when the new process comes in, if his memory is there, he'll use it, and if not, he'll kick somebody out. He'll kick out some of the cache and bring in something he needs. But when the first process comes back, there may be information of his still there in the cache. It doesn't necessarily everything get wiped out. We don't just blank it out for no reason. We leave the cache with whatever data was there, and only ad hoc, as we need new information, ad hoc, we remove things, but there could be some data there. So, if that in mind, we can think about something called processor affinity, which is that you might want that, even though that a certain process always goes to the same processor. Because there he's more likely to find his cache. Because the cache is associated with each chip. Each CPU has its own cache. So I might want processor affinity. Which is that I have an affinity, I prefer to go to the same processor over and over again, even though there are multiple processors.
So that also means that a process could be working with one processor, going back on the queue, then go to the other processor. And then
That could happen, and that could cause, that would be less efficient, that's the point. It could happen that you can go from one processor to the other. So those are just things to think about, that's all I'm saying. So here you see a picture of what I was saying, where. Another possibility is actually, it's sort of what I was saying, which is that CPU has its own cache. Here it's written memory, I think they mean cache here. Or it could be memory, but it could be actual memory, but it could be cache. And anything in my chip, I'll be able to access faster. But theoretically, I could go to either processor and cross access. But it'll be slower. And that's called, I think that's called NUMA. I think it's just a term used for cross-accessing. When you can access the cache of a different processor because it's yours, because it's relevant to this process. Note that memory placement.
MA could be memory access.
What?
In NUMA, MA could be memory access.
Yeah,
And
Non-uniform memory.
yeah,
Maybe.
maybe.
We've just.
It's a major topic. We're not really
Memory.
discussing it. I'm just mentioning if there's a term like that. And I'm mentioning that there is the issue of affinity and that we could have at least certainly theoretically, and in reality, I think they do have such a thing where you can go from one. Of course, this is only going to work. I would propose like this. This is probably not going to work. Well, I'm not sure about this, but it's an interesting question. Will this, I'll leave it as a question. Will this work in a computer with multi-processors, or only in a computer with multi-cores, with one chip with multi-cores? Could you do this if you had two completely separate processors? All right, last slide. Last slide. See, I'm time here. Real-time CPU scheduling. So real-time CPU scheduling can present obvious problems. What are those obvious problems? They're obvious. They're so obvious, we don't need to mention them. But you should think of it. What are they? What does real-time mean?
Doing it.
Real time means we have hard time limits. We need to have a process. When we started this process, we need to guarantee that it finishes in a certain amount of time. So if obviously we're gonna have lots of problems, because if we're gonna say, oh, sorry, you're a long burst, you're gonna have to wait. Well, then how do we do real time? How are we gonna guarantee anything if it's all dependent on our scheduling? So first of all, there's soft real-time system, which is there's no guarantee as to when a critical real-time process will be scheduled. I don't know why it's called real-time then exactly, but it's real-time, but maybe once it is scheduled, then we know when it'll finish. I'm like that. I never, in my mind, I never really understood what soft real-time is. So let's talk about hard real-time. Task must be serviced by its deadline. I mean, soft real-time just means that it's not so critical, but it's sort of.
Like dragging your mouse and then the cursor responding, it's not as important as when you press P that key goes.
Well, no, it's more like a missile system is hard and a mouse is not hard. Because if your mouse is a little slow, you still write your document. The missile, the calculation of the course trajectory correction is slow, then you may have already hit the target. And we're the wrong target.
That's right.
Two types of latencies affect performance: interrupt latency and dispatch latency. The time from the arrival of the interrupt to the start of the service the interrupt. So in other words, real time is usually interrupt driven, which means an interrupt happens, now we need to do this thing. So, but there could be time between when I ask for this thing to be done, where it actually gets scheduled, where it actually start running the service. And dispatch latency is the time for the schedule to take current process off the CPU and switch to another. So interrupt latency is when do I start handling the interrupt? Dispatch latency is when do I actually get the CPU? So here's a picture. What does this picture mean? Interrupt, task T running, determine interrupt type. Right, see, interrupts are related to real time, like I said, as you do the mouse click. Then you have a context switch. And then you can start running it. So this is the interrupt latency.
What's an ISR?
Interrupt service routine. In other words, we got the interrupt, but we don't start handling until here. This context switch is the dispatch latency. Whatever, there's more latent, you don't really have to know these terms. I'm just pointing out the issue involved, the issue involved with real time. That there could be scheduling problems and there could be context switching problems. All right, we'll stop here.
So much.
But we need good.